Hello everyone, welcome and thank you to joining today's webinar. My name is Piotr Stepien and I will perform today Moving to Dynamics lecture. So let's take a look on the contents. So today we will start from simple introduction to dynamics. Then I will introduce to you particular analysis type which can be handled in Midas NFX using very simple example. So we will become familiar with model eigenvalue analysis. I will present you response types and we will take a look deeply inside transient and frequency response. And the main purpose of today's training session is to help you how to perform basic steps for the dynamics. So okay, let's start. So first of all, I would like to start from simple linear static analysis overview. The reason is like following. So today we will consider only a linear dynamic response. So just to remind, let's take a look on linear static assumptions. So as you remember from first webinar session, linear static analysis assume that all of displacements and rotations are small. Supples are not settled, loads maintain original directions as structure deforms, Hooke's law is valid, which means calculated displacements are directly proportional to the applied loads. And there is also no material nonlinearity like hardening or plasticity. Results, of course, can be superimposed as we are using different loads. So now let's simply define what is the dynamics. So using school language, dynamics is a branch of mechanics that deals with motion of bodies under the actions of forces. So motion of the body under the acting force means that we will obtain some response. So body will be moved or deformed according to this acting loading. Usually this response is obtained in time domain. So this response is strictly related to the vibrations. Vibrations are our response, what we observed when the system is subjected to the acting force. So right now I would like to explain to you what kind of vibrations we can consider. So free vibration occurs when a mechanical system is set off with an initial input and then allowed to vibrate freely. So examples of this type of vibration are pulling a child back on a swing and then letting go, or probably hitting a tuning fork and letting it ring. So the second type for the vibration is the forced vibrations, and we can map them when the time varying disturbance, for example load, displacement or velocity, is applied to a mechanical system. And typical examples are vibrations include the shaking washing machine due to some kind of imbalance, vibrating pumps, motors, transportation vibration, and it can be also an earthquake. Okay, now let's take a look on linear dynamic analysis overview. So this graph answers the question what we need to perform dynamic analysis and what kind of output data can we obtain. So to perform any kind of dynamic analysis, we have to specify dynamic load. So load is acting mostly in time, could be applied repeatedly. We can analyze also some irregular loads. So these parameters are necessary to apply for the system. The next is the mass and stiffness. We need these parameters to perform analysis which is called normal mode analysis to get some information about natural frequencies and normal mode shapes, and I will talk about this very soon and I will explain later why we need them. And after this, actually we can choose a required analysis case, for example transient frequency response, to get information about the response. So now we can choose these analysis types. We can perform the calculations to get the required response as displacement, accelerations, or velocities. So all of today's examples we will perform studying the response of single degree of freedom system, which is the most simplest case to introduce to you equation of motion. So you see this equation of the screen. So single degree of freedom system is widely used to describe behavior of simple structures, and you can map these equations in your engineering practice. So if we consider free body diagram, we can write this equation of balance. So, but why we are talking about this? So it's very simple. Midas NFX will perform calculations according to this equation, even for more complex models. So what is important? If we take a look on the screen, you can notice that acceleration and velocity and of course load can vary in time. Mass and stiffness K will be constant during the calculation. Okay, so this is one more thing about the equation of the motion. So as you see, it includes inertial force, damping force, which is responsible for the energy of dissipation. It includes also restoring force. And in other words, we use this equation to describe overall behavior of the structure. And this behavior can be grasped through these three forces. So now, before we go to the particular analysis types, I would like to also remind you types of vibrations. So according to the general equation of motion, we can analyze free undamped vibration. So free means that there is no external load and damping is neglected. We can analyze enforced undamped vibrations. We can analyze free damped vibrations, and of course enforced damped vibrations, which is related to this equation. So next, using Midas NFX analysis features, we will perform this type of analysis according to these vibration types. Okay, let's move to the normal mode analysis. So what is exactly modal eigenvalue or normal modes analysis, and why we need it? So this analysis is a procedure for resonant frequencies of the structure. So now let's define what exactly is this natural frequency. So actually this is the actual measure of the frequency, and this is using to describe the structure when it starts to resonate. Normal mode shape is the characteristic deflected shape of the structure as it resonates. So this type of analysis is used to find out these frequencies due to prevention of the resonance. All you need before to create or maybe perform this analysis has been shown in the right upper corner. So as you see, there is no loading, only constraints, mass and stiffness are required to prepare for your model. So equation for a single degree of freedom system, which is related to normal modes, has been shown above. So from this, we can assume following solution. So we can take a look on this solution. This solution includes a very important parameter, which is called resonant frequency. And as you see, is defined as the square root from K divided by mass. And actually, this is the only one parameter what we are looking for. Okay, so what does the software calculate in model analysis? As I mentioned before, we are looking for the resonant frequencies and related shapes only. So output from Midas provide you natural frequency in radians per seconds, in cycles per seconds, and or in eigenvalue form. All of this data can be collected in the table for easy investigation. So you have to remember that there is no time varying response in model analysis output. So once again, only natural frequency value or shape can be studied. And on the next slide, we see, let's say, example mode shapes. Typically, there are many resonant frequencies in typical structures, so we can obtain many characteristic deflected shapes for each particular frequency. So if you take a look on this cantilever plate, example, we see that if we can obtain first mode at 10.56 Hertz, and actually, as you see, this is a bending mode. The second mode is the second bending mode. We can also obtain torsional modes and others. Everything depends on how many degrees of freedom your structure consists of. Okay, but how many modes, shapes can we obtain? Actually, skipping this FEA theory, we can theoretically there is no limit about this number, but let's say in FEA this number is restricted to the number of number of degree of freedom. So for example, for the single degree of freedom system, this number will be restricted to 1. Okay, to increase natural frequency, you have to increase the stiffness of your structure or system. So we can reinforcing parts at which large deformation occurs, and we can try also to decrease the mass. So this could be more difficult. I'm talking about this decreasing of the mass, but I would like to mention that NFX has got also some module which is called topology optimization, and this module will help you to remove the mass from the system and create optimized model according to the mass distribution. So as you see, we can to increase natural frequency, we have to increase the stiffness and or maybe decrease the mass, or we can do the same both. Okay, so now you see the workflow for the normal modes analysis. So first step is to create geometry of the structure. So actually we can import CAD file or we can create geometry manually. The second step is to create FEM model using, for example, AutoMesh function, or maybe you can use manual element creation tools or features. That point 3, actually we have to set up the material characteristics. So I'm talking about direct input for the structural properties. Or maybe we can use data from database, and of course you have to specify the density to provide the mass to the system. The next step is the setup for the boundary conditions. We can also add additional mass if it is required. We can specify the number of the nodes to be calculated. So now I'm talking about point 6, so which means specify analysis parameters. In this step, actually, we have to go to the dialog box where we can provide requested number for our eigen values, which means mode shapes. So we can specify this directly, or maybe we can input frequency range of interest. As for the Midas NFX 2013, there is a new option which is called Model Assurance Criteria, and this is a very good tool if you want to perform some comparison between experiments. Okay, let's take a look on the first example. So we will create the single degree of freedom model. Now I'm switching to the software, and we will start from the mesh. Now I'm going to create 2 nodes. So I'm using the create command, and let's enter the coordinates 0, 0, 0 for the first node, and for the second one 0.01. Apply. Now I will hide all of these guiders. Actually, we are working in the SI unit system. So as you see at this moment, I just created 2 nodes. And now I'm going to create element command, and we will create some spring to provide the stiffness. So I'm choosing the other. I'm selecting the spring, selecting the nodes. We have to specify proper degree of freedom, and now let's click on the property button and let's add a spring constant. So let's assume it will be 150 newtons per meter. And of course we can change the property to spring. Okay, so we have we just created this this element, and now I'm going to create a mass. So once again I'm going to element create tool, and from options I'm selecting the concentrated mass, and let's assume 2 kilograms for our mass, and please let's click OK. So okay, now I'm deleting this manual mesh, and I'm going to assign the constraints. So I'm clicking on this advanced tab, and let's assign the constraints. So this node will be fixed, fully fixed, and this node will leave translation along the zeta axis. Okay. Okay, so now the model has been created. So we are going to the analysis case. I'm right-clicking on analysis case, and I'm selecting other command. From solution type, I'm choosing the model, and let's add the title, for example, model. And the next step is actually set up for the required number of modes. But as I mentioned before, our example is the single degree of freedom model, so actually we can place 1 in this field. So please click OK. And now I'm going to solve. Let's save our model. So as you see, the calculations are performed, and let's display the results. As you see, we obtained only one result. So actually we can play the animation, so it will be much easier to understand this mode. This is single degree of freedom system, so actually the only 1 degree of freedom is free. So this structure, let's say, can respond only in one direction. That's why it's bouncing on the zeta direction. And required normal mode frequency, actually you can find there. So it's 1.37 Hertz. Now I would like to show you the eigenvalue analysis result table. And I mentioned about this during the lecture. So in this table we can find out all of parameters what we need from this type of analysis. So as you see, eigenvalue has been calculated, and it equals to 75. And our natural frequency is located there in cycles per second, or maybe in radians per second. So we can choose it we can choose the result from this table. Okay, let's go back to the presentation at this moment. So as you see, this is the slide with the results for, which come from normal mode analysis. So I created a system with mass 2 kilograms and K with 150 Newton per meter, and we can compare the theoretical result with the results from Midas NFX. So actually this is a simple calculation, so there is almost no difference. Okay. Now let's talk about the response methods. So basically, response methods can be divided into 2 categories: transient response analysis and frequency response analysis. So the difference between them is like following. So external loading can be, but is applied as a function of time for transient, and as a function of frequency for the frequency response. So typical examples are impact loads for the transient, so we will obtain also the response in time according to applied load. For frequency, analysis, we always apply harmonic load with different frequencies. So a calculated response provides us information about displacement due to applied frequency. Response for frequency analysis is a steady state response, so there is no variation according to time. So next slide depicts dynamic analysis dividing according to used solution algorithm. So we can consider algorithm based on the direct integration method or modal superposition method. So as you see, both of response analysis, I'm talking about the transient response and frequency response, can be analyzed using both methods. And it's related for, it could be used for the linear and nonlinear analysis. But if we take a look on this modal superpositions method, actually we can perform only linear, let's say, dynamic response analysis. So these both methods are implemented in Midas NFX, and today I will use only direct method only. Maybe for the next webinar we will show you the examples using the other method. Okay, as I mentioned before, transient response analysis is executed in time domain. So if we take a look on the graph to the right, we see to run the analysis we need a load which will be a function of time. We can also add also a damping to the system, as of course we need it, and calculated response will be obtained in the time domain. So in Midas NFX, analyzed structures can be subjected to the nodal loads like velocities, displacement, and accelerations, and we can apply them directly on the structure with the reference to the time function. So, but there is also, let's say, another way to apply dynamic load. I'm talking about static loads, which can be converted to dynamic loads using this analysis control feature. So a typical examples for the converted loads are the gravity, pressure. So there is always a problem to apply them in the time domain. So we can use this tool to apply them for our structure. Okay, now I would like to show you how to perform analysis considering free undamped vibrations. So as you see on the screen, the same single degree of freedom system. And as you remember from modal analysis, we obtain only natural frequency information. There was no time response. So as you see from the solution, we need to specify initial conditions this time for our single degree of freedom system. So let's assume the velocity in the opposite zeta direction. And let's switch once again to Midas NFX. Okay, so now I'm saving the model with a different name. So I say free vibrations. And now I'm going to load and boundary conditions. I'm clicking on the dynamic load, and let's add to the system initial nodal velocity. I'm selecting the bottom node, and let's add -1. So this will be our initial condition. We can also change the name for the load set as initial velocity. Okay. And let's go to the analysis case. So for this case, I will delete the previous one, and I will specify the new one. So we will use direct transient response. Let's add the title, vibrations, and let's drag and drop the initial velocity under the proper branch. So in this case, we have to go to the subcase control and we have to specify the time step. I will talk about this a little bit later. So at this moment I will add some values. Let's say time range. Let's assume 6 seconds and the 160 number of time steps. Close. And let's perform the calculations. So the model has been already calculated, and as you see, Midas NFX in 2013 version has been improved, and it provides now some interactive graph, so we can investigate the results during the calculation process. So as you see, we achieved the graph for the free vibration, and we can easily check the response for our single degree of freedom system. Okay, let's go back to the presentation once again. Okay, the next case I would like to show you is the let's say damping definition. So if we provide to our equations viscous damping, the formula becomes like the following. Generally speaking, there are three possible solutions according to this equation. So we can consider critically damped case, overdamped case, and underdamped case. And to imagine these three cases, actually a swing door with dashpot closing mechanism will be a good analogy. So if the door oscillates through the closed position, it is underdamped. It is underdamped. So if it creeps slowly to the closed position, it is overdamped. And if it closes in the minimum possible time with no overswing, actually it will be critically damped. So next slide explains the response for critically damped case, and this will happen when let's say defined damping coefficient will be the same as critical damping coefficient. So you see the definition there. So the formula for single degree of freedom system has been shown below the graph. As you see, this critical ratio equals to mass multiplied by omega n multiplied by 2. And from this graph we see that the system is going to achieve the balance very rapidly. For overdamped case, which will take a place when provided damping will be more than critical, system will achieve the balance very slowly. Third case response has been shown on the next slide, and actually we are generally only interested in this case. So when damping of the structure is less than critical, the solution becomes this. So this is the solution for the underdamped case. So omega d represents the damped natural frequency of the system, and zeta is called the critical damping ratio. So in Midas NFX, dependent on case, we are using damping ratio or current damping value. So we can remember that in most cases, zeta is less than 10%. But anyway, so we can ask the question, for example, what level of damping should we use for our models? So actually, this is a very rough rule of thumb using critical damping ratio for this example, and I can provide you some examples. Like for example, like for composite structures, actually we can use 3 to 10% of critical ratio. Rusty structures has got ratio from 5 to 10. Metallic bolted structures 3 to 6. But anything over 10% actually is reaching the limits of linear analysis. So now you see the underdamped case graph, and as we see, in this kind of response, amplitude is a function of damping, so you have to remember that. Okay, there are 3 damping types we can use in Midas NFX. So first one is the viscous damping. So mostly we will use damping ratio to define damping to define it, or maybe we can use current damping value. The second one is the structural overall, or maybe material based damping. And the third one is the model damping, which is used in the model method, and actually is the same like viscous damping, but it is linked to each mode shape. And now you see the workflow for the transient response analysis. So actually it's almost the same. So we have to prepare the structure, we have to create a finite element model. Of course, material and boundary conditions should be provided. But according to load, we have to specify load in the time domain. And of course, if we want, we can specify the damping. And there is one important thing according to the transient response. Actually, we have to provide proper time step for our analysis. So for the time step, actually, it's generally good to use values smaller than 20 times less of the working frequency of external load in order to reflect both the maximum and minimum load values. So, for example, when our force includes our force of 100 Hz is being applied, calculate time step should be smaller than 1.01 divided by 20. So this is actually the simple rule for the time steps. Okay, let's take a look on the transient response example. I'm switching once again to minus NFX. Let's save the model as enforced damped vibrations. And this time I will create second element. So I'm going to create, and we will add the damper to the system. I'm selecting the nodes. I'm choosing the proper degrees of freedoms. And let's specify the value for the damping. So actually we'll use 10% of critical damping. So in this case it will be 3.464. So you can check this if you want to make these models by yourself. This webinar will be recorded, so actually we will provide it to you. Okay, so now I'm clicking OK. So damper has been added to the system, and now we have to create a load. So now I'm going to create time-dependent nodal force. And as I mentioned before, we have to specify time dependency function. So we want to analyze, so in this case, I will create a force which will be applied at the natural frequency. So we will observe the resonance, and I will use the template for that. Now I'm pasting, and let's change the name to force at natural frequency. Let's select the node. And let's add the value. Of course, we can change the dynamic load set. Load, okay. So now I'm going to create another analysis case. Let's say transient. Okay. you have to remove from the dynamic load this initial velocity, and let's create let's define the time step. So okay, time range. Okay, so time duration in this case will be 10 seconds, and the number of time steps 277, let's say. And let's perform the calculations. Okay, so we obtain this graph. But as you see, I think I made some mistakes, so I have to check it, because it seems that I forgot to add function. So I forgot doing this step. That's why we achieve the results like damping, like underdamped vibrations. So let me show you the proper result for the previous example. So now you see, this is the resonance what I mentioned before. So sorry about that. So let's go back to the presentation. And now let's talk about the frequency response. So what is actually the frequency response? So this is a technique to determine the steady state response of a structure to sinusoidal, let's say, or harmonic loads of known frequency. And you can imagine this as response to a structure on a shaker table. Or for example, you can imagine some kind of exciter of wave generator, and adjusting the frequency input to the table, it will give us some kind of range of responses. So for this type of analysis, we will define excitation load as a frequency load. Response, of course, will be in the frequency domain. So this type of analysis is widely used to analyze superstructures, some facility equipment, rotary machines like compressors, engines, pumps, and turbo machinery. So equation for this system look like the following. So in this case, load, as I said before, will be provided to a structure as a harmonic with range of input frequencies. Now, if we take a look on the solution, we can consider few response possibilities. So when the driving frequency tends to 0, we will obtain the static solution. When driving frequency will be equal to the natural frequency, this term will be 0 and no damping will present to the system. And of course, we will obtain this term, which controls the scaling of the response, and from that we will derive dynamic magnification factor. So let's take a look on the next slide. And you have to be familiar with two important terms. First one is the phase fleet, which is defined like that. And the second, let's say, parameter is a dynamic amplification factor, which controls the scaling of the response, and this is widely used for the to describe your response very quickly. So if the ratio of the frequencies will be less than 1, amplification factor will become 1 and you will obtain the static solution, and the response will be in phase with the force. When this ratio will be much more than 1, amplification factor became 0 and you will obtain no response, and this phase angle will get the opposite sign of the force. But if we provide to the system a ratio which will be close to 1, actually we will get the resonance. So there is also one thing you're supposed to know about the frequency analysis. So computer responses are the complex numbers, and they are defined as magnitude and phase. Or maybe you can define them as real and imaginary components, which are the vector of components of the response in the real imaginary plane. Loads can be also treated as frequency-dependent loads according to real and imaginary plane, or maybe magnitude and phase. So frequency response analysis overview looks like following. So in this case, we have to calculate the frequency range. So Midas NFX allows to provide few methods to define this frequency range. So discrete, linear, and logarithm. And actually, this is the main difference between transient response. So let's take a look on the next example. So I'm deleting this analysis case and I'm going to the loads, and this time I will provide frequency dependent nodal force. So I'm selecting the node, I'm creating the unit load, and we will use magnitude and phase dependency. So for magnitude, let's say define 1 and leave the constant phase for the angle. So okay, and let's specify, let's create the analysis case. So this time we will perform direct frequency response. And let's define the frequency set. Now I'm adding the title. From frequency method we will choose linear, and we provide the range from 0.01 cycle with the same increment, and number of increments will be set up to 300. Okay, we add this. Okay, let me check once again. Okay, everything seems to be fine. Oh, sorry, I have to check on output control. So right now I want to obtain displacement results, let's say in absolute values. So I'm clicking OK, and let's solve. So as you see, we obtain the frequency response graph, which means for the natural frequency, which is 1.137, if I could remember, we obtained the maximum displacement as 0.333. So as you saw, the driving frequencies range was defined from 0 up to 3 Hz. And if you put this data to the equations, you will see that amplification factor looks like 5. So static response for our system is 0.006 meter. And if you multiply this by the amplification factor, the peak response will be like that. And this occurs in the natural frequency. So if we compare this two graphs, actually you see that we obtained the same peak response for both analysis types. So if you want to learn more about the dynamic analysis, please visit the YouTube channel So you will find a lot of videos, tutorials, presentations according to Midas NFX. So thank you for today's webinar, and my colleague Cyprian will inform you about the next webinar session.
Hello everyone. I hope you follow everything during this webinar. It was a bit theoretical, but you'll have the video, you'll have the demo and the PDF, so you can try by yourself at home. So I'd like to tell you again that if you want to see more examples, more tutorials about dynamic analysis, for example, you can go on our YouTube channel. So just go on the address which is written here on the screen, and you will find a lot of user study, user talking about their own experience in NFX and tutorials and everything. So this was the webinar today about dynamic analysis, and tomorrow we will have another webinar about CFD analysis that I will conduct, and it will be very interesting, so I hope everyone will join also this webinar. I will show you how to perform very good CFD analysis and how to apply the boundary condition, how to set the walls, and even show you some examples of more high-end CFD analysis, like, for example, analysis on pump equipment using moving mesh or fans. This kind of analysis can all be performed with NFX. So we'll see that tomorrow.